Hello, grade 12. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Uabudiwa Sos Ugobela Wemet. And without any further ado, let's look at these questions that we have here. Okay, so we are doing structured questions, and then we are still on the topic momentum and impulse, just to get ourselves rolling, and then also being able to understand the concept more clearly. Then this is how we escalate until we get to those exam type questions and then those difficult questions. So this is just a method to show you guys that even if when you are picking the book there and you want to study, this is how you should go about it. Start with the easier questions, then slowly build up to the difficult questions, right? So in that way, you make sure that you gain momentum as you study. So no pun intended there. Then, okay, question 2 says a ball of mass 0.35 kg strikes a wall with a speed of 20 meters per second, rebounding with a speed of 18 meters per second. The collision with the wall lasts for 0.05 seconds. Then 2.1 says calculate the initial momentum of the ball, right? Then let's see the scenario that is taking place here. So representing it in terms of a diagram, this is what is happening. This is a ball of 0.35 kg thrown at the speed or projected at a speed of 20 meters per second. And then it hits against the wall, then rebounds at a speed of 18 meters per second, right? Then if we are to assume that the ball was thrown east, then that means after hitting against the wall, it rebounds to the western direction, right? So this is just a scenario for what took place. Then 2.1 says calculate the initial momentum of the ball. To do that, we say momentum initially, that's mass multiplied by its velocity. What is the mass? We are given that it is 0.35. The velocity initially, that's 20. When we multiply the two, that's 7 kg meters per second. But then remember, we assume that the ball was thrown east, so I need to indicate that this is in the eastern direction. Why is it important that I show this? Remember, momentum is a vector, so it has both magnitude and direction. Then for 2.2, so this was 2.1. For 2.2, we have PF is equals to mass multiplied by V. What is our mass? That's 0.35. And then our velocity, that's 18. When we multiply the two, we get a value of 6.3 kg meters per second. But then to which direction? West. Right. Now, in 2.3, they say calculate the change in momentum of the ball. How would we calculate the change? Understand that the change in momentum is the momentum finally minus the momentum initial. What is our momentum final? It is 6.3 kg meters per second west. Now, if we are to say that we choose east as positive, that means our west needs to be negative. Right. So, since when the ball rebounds against the wall, it moves to the opposite direction, which is west. We need to indicate our 6.3 here as a negative, right? It is going in the negative direction of the initial motion. Then that's negative 6.3 minus 7. Now we get negative 13.3 kg meters per second. So that means we have to conclude now. Therefore, our change in P is 13.3 kg meters per second west. So our change in momentum is in the western direction. Note that with the change in momentum, it will always be in the direction of where the net force is, right? So after rebounding against the wall, where is the object moving? It is moving in the western direction. Therefore, if in our change in momentum needs to be in the direction of the motion, right? So remember, according to Newton's second law of motion, in terms of momentum, we say that the net force is equal to the rate of change of momentum in the direction of the net force. So the direction of the net force will always be in line with the direction of the object there. That means even your change in P needs to be in that same direction, right? So this is how we get that. Now, 2.4 says draw a vector diagram showing the initial momentum, final momentum, and change in momentum, right? Okay, but before we go there, let's just go back to 2.3. Just for option number 2, I'm just thinking about it now. This is how you could also solve that one. Remember, you have the formula M VF minus VI. So for someone wondering that would I still get it if I just used the formula as I know it? Yes, you would still get it. What is your mass? This is 0.35. And then your VF, you need to note here, the 18 meters per second is now in the western direction because your ball has rebounded. So you need to indicate your 18 here as negative 18. So that's the only part that you need to understand there. Then minus 20. When you punch all this in your calculator, it should give you negative 13.3 kg meters per second. Right. So 13, negative 13.3 kg meters per second. Then we understand that's 13.3 kg meters per second. And then west. Right. Okay, good. So whether you use this, knowing that your change in P is PF minus PI, or you simply just break it into a formula and then substitute again the values that you were given, you'd still get the same answer, because if you look at this is still the same thing. This has the same meaning. If you say M times VF, that's your PF. If you say M times VI, that's your PI, right? Then now, 2.4 says, draw a vector diagram showing the initial momentum, final momentum, and change in momentum of the ball. So let's indicate this. So we have our dot here, which is the tail. Remember, when we are drawing a vector diagram, it is always the head to tail method or the tail to head method. So we have the tail there, and then it's going all the way to the head. So this will indicate our initial momentum, right? And then this here will indicate our final momentum. Now, if you can pay attention, you can see that my momentum finally is shorter than my momentum initial. Why? Because according to our calculations, we saw that this was 7 kg meters per second, and this was only 6.3 kg meters per second, right? So the final momentum was actually lower than the initial momentum. Then your vector diagram needs to show that, right? Remember, a vector shows both magnitude and direction. So your magnitude is shown with the length of the lines, and then your direction is shown by the arrows there, which is the head. Then now, when you draw the change in momentum vector, it needs to always start at the head of the initial momentum. So now, this is where we'll start. That means your tail will be here, and then your head will be going all the way to the west, right? Why? Because remember, the change in P was in the direction of west. It was in the negative direction. So it was negative 13.3. Now you can see that it is longer, and then it is a sum of both of this. If you can just add 7 and 6.3, you get 13.3, right? So the negative is just indicating the direction. So the direction was in the western direction. So you need to indicate that this one is change in P. So this is how they expect you to draw your vector diagram. So you just indicate the directions. The PI was in the eastern direction, the PF to the western direction, and your change in momentum was in the western direction, right? So it starts from the head of the PI all the way to the head of PF, right? Then 2.5 says state Newton's second law of motion in terms of momentum. So I had already discussed this. Then this is how you This is how you define it. It needs to be in line with this equation here. F net is equals to change in P over change in T. Then if you can remember this formula, it becomes very easy to define. You just mainly say Newton's second law of motion. Newton's second law of motion states that the net force of an object is equal to the rate of change in momentum of the object in the direction of the net force. In the direction of the net force, right? Then that's how you define it. Newton's second law of motion in terms of momentum states that the net force of an object is equal to the rate of change in momentum of the object in the direction of the net force. So if you have watched my previous video, you saw all these definitions, right? So that's where I started, right? So I will drop a link to link you to the first video that I did on momentum and impulse this year, and then you will see all these definitions. Then 2.6 says calculate the net force acting on the ball during its collision with the wall, right? So now we are supposed to calculate the net force. Then how do we calculate the net force? We use the very same formula here, change in P over change in T, right? Then remember, we just calculated our change in momentum in 2.3. So that's what we're going to use. But then note this, it's saying the net force acting on the ball during its collision with the wall. So the net force acting on the ball, right? What is the net force acting on the ball? We do understand that the net force acting on the ball will be the force that is exerted by the wall on the ball. So considering Newton's third law, we do understand that when the ball hits against the wall, it is exerting a particular force on the wall. But then the wall is also exerting the same magnitude of force, but in the opposite direction. So we can conclude that the force of the ball on the wall is equal to the force of the wall on the ball. So that's our Newton's third law. So object A exerts a force on object B, then object B exerts the same magnitude of force to object A, but in the opposite direction. So in order to calculate that, remember our change in P was negative 13.3, right? And then a change in T, that's 0.05. So when we read here, they say the collision with the wall lasted 0.05 seconds. Then if we say negative 13.3 divided by 0.05, that will give us negative 266 Newton, right? But then the negative here, this simply states that F net is 266 Newton west, right? So we do understand that the wall here will be exerting a force to the west on the ball, right? So because remember the ball was coming east like that, and then it hits against the wall, then it will experience an opposite force from an oppositely directed force from the wall. So hence we have this negative here. So our F net is 266 Newton west. Now let's look at this. The question below here says 2.7, determine the net force acting on the wall during the collision. Justify your answer. So that means, according to our Newton third law, we just said that the F net now will still be the same magnitude. That's 266 Newton. But this time it will be going to which direction? East. So the wall exerts a force of 266 Newton in the western direction to the ball, but the ball exerts a force of 266 Newton in the eastern direction to the wall, right? So that's how you go about it. Then how do you justify that? You just say Newton's third law. Newton's third law. So when object A applies a force on object B will apply the same magnitude of force, but in the opposite direction. Okay, let's look at question number 3 then. It says, calculate the change in momentum of the car. We are given the statement here. A car of mass 1,200 kg accelerates from 20 meters per second to 40 meters per second. So that means it is increasing in velocity. In what? In 8 seconds. So we are given the VI to VF, and then we are given change in time. Then calculate the change in momentum of the car. For 3.1, we have to use the formula change in P is equals to M VF minus VI. What is our mass? We are given that it's 1,200. Then our VF, that's 40. So we do understand that this is in the same direction. So if it is accelerating, that means it is still moving in the same direction, right? Then 40 minus 20. Then all you have to do is punch all that in your calculator. Then this will give us a value of 24,000 kg meters per second. So if you are assuming that it was going east, then let's just say east. Then 3.2 says draw vector diagrams to show the initial momentum, the final momentum, and the change in momentum. So note this. The initial momentum, if we are to indicate here, the starting point, which is our tail, and then this would be the initial momentum, right? But then, since the object is still moving in the same direction finally, then this is our final momentum. So we do understand, because of the values here, that our final momentum will just be slightly shorter than the initial momentum. Because remember, it was it will be slightly larger. So we do understand that because of the values here, our final momentum, if we had to calculate, would be larger than the initial momentum. Remember, it was at a velocity of 20. Now it has accelerated to a velocity of 40. So we need to indicate that our final momentum is larger, right? Then there we go. So this is our PI, and then this is our PF. Now, how will we indicate our change in momentum? So you do understand that our change in momentum will always the change in momentum begins from the head of the initial momentum. Then now, because this is going in the same direction, but then it is accelerating. So we need to indicate that it is in the same direction of the final momentum, like that. But then where we understand that our change in P is PF minus PI. So obviously, if you have to subtract the two, you do understand that now the change in momentum will be lower, because this is just a difference in the final momentum and initial momentum. So the change in P would be starting from the head of the initial momentum all the way to the head of the final momentum. So this would be your change in P here. This would be your PI, your PF, your change in P. So this is how you draw the vector diagram to show the initial, the final, and the change in momentum of the car. So I hope that makes sense. Now 3.3 says calculate the net force acting on the car. So to calculate the net force, we have F net. So this is 3.3. We have F net is equals to change in P over change in T. Right. We have already calculated our change in P. That's 24,000. And then time, we are told that this happened over a period of 8 seconds. So if we say 24,000 divided by 8, this gives us 3,000. 3,000 what? Newton. To which direction? East. Okay, so we have question 4. It says a football player kicks a soccer ball of mass 450 grams. So what we are supposed to do with this 450, we divide it by 1,000 because we can see it is not in the desired SI unit. So remember the trick with this, immediately you see that something is not in the desired SI unit, convert it right away. Then they say he kicks a soccer ball away from him with a speed of 15 meters per second. His foot is in contact with the ball for 0.6 seconds. The change in momentum of the ball is 8.1 kg meters per second away from the play. Right. Now, 4.1 says calculate the initial speed of the ball. So let's see the information that we have. We have mass, it's 0.45 kg. And then we are given our velocity finally because we are to calculate the initial speed of the ball. So this is the velocity finally. So 15 meters per second. Then VI, we are looking for that. And then change in P is 8.1 kg meters per second. Then to calculate, we just mainly use the formula change in P, M, VF minus VI. What is our change in P? That's 8.1. What is our mass? It's 0.45. And then our V finally, that's 15. Then V initially, that's what we are looking for. Now, what you want to do here is first divide out with the mass here, 0.45. And then 0.45. If you say 8.1 divided by 0.45, that's 18. Then you have 18 is equals to 15 minus V initially. Now what you can do is take this over to the side. So that's VI is equals to 15 minus 18. So your VI will be equals to negative 3 meters per second. Right. So now we can understand the scenario here that the player, this was the player, and then this was the ball coming towards him at a velocity of 3 meters per second. So because it's negative, we can tell that the direction here was west. And then the player was facing the eastern direction. And then now, initially, the ball was coming at him at 3 meters per second. Then he kicks the ball back at 15 meters per second. So that means our VI is 3 meters per second west, right? So the scenario that took place is the ball coming towards him, and then he kicks the ball back with a greater velocity. Then now they say 4.2, calculate the magnitude of the net force of the player's foot on the ball. So to calculate that, we have F net is equals to change in P over change in T. So to calculate the magnitude of the net force of the player's foot on the ball, right? So we have the change in momentum of the ball, that's 8.1, and then divide that by change in time, that's 0.6, right? So we have 8.1 divided by 0.6, that's equals to 13.5 newtons, right? So because the net force of the player's foot on the ball, the net force of the player's foot on the ball, right? It's 13.5 newtons east, because the player's foot is on the eastern direction when he kicks, right? It's kicking in the eastern direction to the right. So that's the net force that he exerts on the ball, right? But then the net force that the ball exerts on the player's foot will be 13.5 newton west. So understand that. Okay, so now to do questions from past exam papers. We have question 5 here, which is an extract from physics paper 1 NSCE, Feb, March 2014, which is in question number 4, right? Then we are given here the momentum versus time graph of a car, originally moving horizontally east, is shown below. Now, when you are given a graph like this, this is what I want you to understand. If your graph is above the x-axis, this indicates that your momentum is still in the eastern direction. But then the moment your graph is below the x-axis, this indicates that your momentum is now in the western direction. So this is what you need to understand with your momentum versus time graph. Then 5.1 here says, write down the definition of momentum in words, right? Now, if we are to look at the formula P is equals to m times v, from this can help us to actually deduce the definition of momentum in a way that we can say that momentum here is the product of the mass of the object and its velocity. So that's how we define momentum. We just say momentum is the product of the object's mass and its velocity, right? So for 2 marks, that's how you are supposed to define it. Then 5.2 says the net force acting on a car is 0 between t 10 seconds and t 20 seconds. Use the graph and the relevant equation to explain why this statement is true. Now, looking at time t0, t10 to t20, we can see that our graph here is constant, right? So it is just horizontal like that. So which indicates that our momentum is constant. Now, if our momentum is constant throughout 10 seconds to 20 seconds, this proves that if we can just calculate our change in P and we say PF minus PI, this would be 50 for PF and then still 50 for PI. So momentum finally minus momentum initially, that would be 0 kg meters per second. So constant momentum means that our change in P will be equals to 0. But then remember, F net is given as change in P over change in T. So if our change in P is equals to 0, that means our F net will be equals to 0 newtons as well. So which is why now we can see that our net force there is 0. So we have proven using relevant equations to prove that the statement there is true. So number 1, we deduce that the line here is constant. So we have a constant straight line horizontal graph, which indicates that our change in P is equals to 0 kg meters per second. And then since our change in P is 0, that means our F net is also equals to 0 newtons. Right. Then 5.3, so this was 5.2. And then 5.3 says calculate the magnitude of the impulse that a car experiences between t 20 seconds and t 50 seconds. So to calculate the impulse, this is how we go about it. You will remember that impulse is equals to F net delta t, right? But then we have what we know as the impulse momentum theorem, which simply states that the impulse of the object is equals to the change in the momentum of the object. So that means, in other words, the impulse here can be equated to the change in momentum of the object. Now, looking at this, we can tell that we are given the time from t20 to t50. So the difference in between the times is 30 seconds. So from 20 to 50, that's 30 seconds in between. But then in order to calculate the impulse, we need the F net. And from the statement and all the information in the graph, we can see that we are not given the F net. Remember, the F net between 20 to 50 seconds is no longer 0 because you can see this is not a constant horizontal graph. So we do have a particular F net from this time here to that time. Now, we can see that if we were trying to calculate the impulse using this formula, it will be a bit tricky because we cannot, in a way, calculate our F net. Now, that means we can use the impulse momentum theorem to say that if our impulse is equal to the change in the object momentum, that means we can try to calculate the impulse using change in P, using the change in momentum. Then we want to say M is Vf minus Vi. Now, for all of this, we do have the information. What is the momentum? Remember, change in P can be indicated as the momentum finally, which is Pf minus the momentum initial, right? We do have the momentum finally, which is the momentum at time time 50 seconds, so which is negative 120. And we do have the momentum initially, which is at time 20, that is 50 kg meters per second. Right, so negative 120 minus 50, that's equals to negative 170 kg meters per second, because we just calculated the change in momentum. But remember, if we are to say we are calculating the impulse, we need to change this SI unit here. So this would be 170 Newton second. And then since it's negative, we need to indicate that the impulse is in the western direction. So that's 170 Newton second west. Right. So using the change in momentum, we've found a way to calculate the impulse. And then if you're wondering where I take this SI unit here, it comes from here. Remember, F net is in newtons, and then your change in time is in seconds. So the SI unit for impulse would be Newton second. Now, to calculate 5.4, it says at t is equals to 50 seconds, a car collides with a buggy, which has a momentum of 70 kg meters per second. Now they say use the information from the graph and the relevant principle to calculate the momentum of a buggy after the collision. So, okay, let's calculate that. Now, we can use the formula that goes change in momentum initially is equals to change in momentum final. Now let's go ahead and say we are taking east as positive. Right. Now, what is the momentum initially for the car? Then plus the initial momentum for the buggy. This would be equals to the momentum finally for the car plus the momentum finally for the buggy. Right. Now, to substitute the momentum initially for the car, can just go back where it started, just at t 20 seconds, because remember, this is in between, or this is at 50 seconds, meant to say, so not 20. This is at 50 seconds. So this means this is our initial momentum here at 50 seconds, and then we can tell that it is negative 120. So substitute negative 120 there. Then what is the initial momentum for the buggy? They told us here. It collides with a buggy which has a momentum of 70 kg meters per second. So we can substitute the 70 in here. Then what is the momentum finally for the car? We can see that here the car collides with the buggy, and then now it returns back to a momentum of 50 kg meters per second. So this here indicates a collision. Then now we have 50 plus the final momentum for the buggy. That's what we are looking for. Now, if we are calculating here, that's negative 120 plus 70, it's negative 50, and then we have 50 here, then PF for buggy. Now we can take this 50, transpose it over to this side. That's negative 100 kg meters per second is equals to PF of buggy. Right. Now, to interpret that, we know that the negative here is representing the negative direction, which is the western direction. So the PF for the buggy, the momentum after the collision, is 100 kg meters per second. To which direction? West. Right. And that's how you could indicate that. So let's proceed. We have question 6. It says the graph below shows how the momentum of car A changes with time just before and just after a head-on collision with car B. Car A has a mass of 1,500 kg, while the mass of car B is 900 kg. Then we are told that car B was traveling at a constant velocity of 15 meters per second west. Pay attention to that. We are told that the direction there is west. Now, before the collision, look at this here. They say take east as positive and consider the system as isolated. Then we are given the momentum versus time graph for only car A. Then we are given our cardinal points, which I've already explained that in most of our exam questions, we'll be given these cardinal points so that we avoid using left, right, but instead we'll be using east and west as our directions. Then they say use the information in the graph to answer the following questions. Then 6.1 says calculate the magnitude of the velocity of car A just before the collision, and we are given 3 marks. So we know that our marks usually detail to us the effort that we should put in there. Magnitude of the velocity of car A. Let's check here. We are given the momentum here. This is the momentum before the collision. So this here is the momentum before the collision all the way. Then when you see this slanting line here, this means this is where collision takes place, right? And then here, this is after collision. So we can put it like this. This is before collision. This is during the collision. And here, this is after collision. Now, we are supposed to calculate just before the collision, right? So, meaning we can say P is equals to M times V. What is our momentum? That's 30,000. But when we go back here, remember we were given the mass for car A. They say the mass for car A is 1,500 kg. So, that means we can substitute 1,500 and then V. Then divide both sides by 1,500 in order to calculate our velocity. Then 30,000 divided by 1,500, that's 20 meters per second, right? And just like that, you have your 3 marks, right? And then don't forget our velocity there is a vector, so it must have both magnitude and direction. So that's 20 meters per second east, right? So note that if you don't write the direction, you forfeit the mark. Then 6.2 says, calculate the velocity of car B just after the collision. So the velocity of car B just after the collision. Now, this is how we are supposed to do that. Remember, we have the formula that goes sum. So the formula for the principle of conservation of linear momentum. So sum of momentum initially is equals to sum of momentum finally. Then we have momentum of A plus the initial momentum for B is equals to initial final momentum for A plus final momentum for B. Now, what is the initial momentum for A? It's 30,000, right? But what is the initial momentum for B? For that one, we need to consider the calculation here or consider the information. Then to say that our initial mass, remember, momentum is mass multiplied by velocity. So our initial mass or our mass is 900. Then our initial velocity is 15 meters per second, but where? West. So we need to indicate it as a negative because we took east as positive. Then is equals to, what is the momentum for A after the collision? So let's look at this. Remember, this was before collision, during collision, and after the collision, the momentum is 14,000. So we substitute 14,000 here. Then plus, to look for the velocity of B, we can just substitute the mass for B and then multiply that by the velocity V2F. Now, if we punch all this in our calculator, that's 30,000 plus 900 multiplied by negative 15. So all this will give us a value of 16,500. We can just right away transpose this 14,000. So minus 14,000 is equals to 900 V2F. Now, what is 16,500 minus 14,000? That's equals to 2,500. Then we still have the 900 here. V2F, if we divide both sides by this 900, then our velocity finally for car B is 2.78 meters per second. Since it comes out as a positive, that means it's east. Now, what is this telling you? Car B was moving west at a velocity of 15 meters per second west. It collides with car A, and then now it's moving at 2.7 meters per second east. So that means this is a case where car B rebounds after colliding with car A, and then now it moves in the opposite direction at a lower speed, right? So we can see that. Now let's proceed to 6.3. It says, calculate the magnitude of the net average force acting on car A during the collision, and then we are given 4 marks, right? So how are we supposed to calculate that? We have here the formula for Fnet is equals to change in P over change in T, right? But then remember, change in momentum is momentum finally. We are calculating for car A, so that's momentum finally for A, and then momentum initially for A over change in time. So we will be using the graph here. Then what is the momentum finally for A? It's 14,000. What is the initial momentum? It's 30,000. Then divide that by what? We want to find the time in which the net force takes to act on the object, right? So we want to find that time in between the collision. So remember, we said this is during the collision. So we want to understand the time that the collision takes, right? So it's 20.1 to 20.2. So the difference there, it's 20.2 minus 20.1, which tells us that the collision lasted for 0.1 second. Then if we say 14,000 minus 30,000 divided by 0.1, we get 160,000, negative 160,000 newtons. So since it's negative, we should conclude Fnet is equal to 160,000 newtons west. Remember, we took east as positive, so if we get our value as a negative, it indicates that it is in the western direction, right? That's how you were supposed to solve that for 4 marks. So you'd get yourself those decent marks. It's about 12 marks just to solve your question 6. So pretty nice. Then let's go to question 7, which is an extract from Eastern Cape Physics paper 1 September 2014, also taken from our question number 4. A car of mass 1,500 kg is stationary, meaning the velocity is 0 at that particular time. At a traffic light, it is hit from behind by a minibus of mass 2,000 kg, traveling at a speed of 20 meters per second. Immediately after the collision, the car moves forward at 12 meters per second. So we are showing the scenario here diagrammatically to show that the car was stationary at the traffic light with a velocity of 0, as I've told you. Then here we can see our minibus taxi coming from behind, and then it hits the car from behind. Now the car is moving at a velocity of 12 meters per second, but now we are no longer given the velocity of the minibus taxi. Now 7.1 says, state the law of conservation of linear momentum in width for 2 marks. So at this moment in time, we already know how to define that. We just simply say the law states that the total linear momentum in an isolated system is conserved, right? Is conserved. Now, I am aware that some documents may write it as remains constant, and then sometimes they might just say stays the same. So either way, you'd be correct. the total linear momentum in an isolated system is conserved, or it remains constant, or you can say stays the same. All this mean the same thing. Then 7.2 says calculate the speed of the minibus immediately after the collision. Now, the hint with these questions is that if they ask you to state the law of conservation of linear momentum, and then right below there's a question on calculation, it is quite easy to just know that they want you to apply the law of conservation of linear momentum. So just put it in the back of your mind that that is in a way a hint on its own, right? Then here we can see that this is case number 1, whereby two objects are moving separately, they collide, and then they still move separately after the collision. So that means we are supposed to have M1 V1 plus M2 V2 initially, and then here we have M1 V1 plus M2 V2 finally. Now, what is the mass of the car? We were told that it's 1,500. What is the velocity of the car initially? It's 0. Then we have plus. What is the mass of the minibus taxi? That's 2,000. And then its velocity is 20, right? Then right here we have the mass, again 1,500. Then the velocity is now 12. Then plus the mass of the minibus, that's 2,000. Then we are looking for the velocity V2. Now, if we punch all this in our calculator, obviously here we're going to get 0, 40,000. Then 1,005 multiplied by 12, that's 18,000. Then we have plus 2,000 V2. Now we can take this 18,000 over to the side. So that's 40,000 minus 18,000. Now we get 22,000 is equals to 2,000 V2. If we divide both sides by the 2,000, now our V2 is equals to 11 meters per second. So what happened here? From this, we can tell that the velocity of the minibus taxi decreased after collision. So it was moving at a velocity of 20 meters per second, and then after the collision, now it is moving at a velocity of 11 meters per second, which is now lower than the initial velocity. Now 7.3 says the driver of the minibus is not wearing a seatbelt. Now we know what happens when you're not wearing a seatbelt. Describe the motion that the driver undergoes immediately after the collision. We say the driver will continue in the initial direction of the taxi. In the initial direction and motion of the minibus, right? Of the minibus. So now we do understand that if we have our driver here and then they collide, they will just continue in that very same direction because of what we know as inertia, right? So what is inertia? We say this is the resistance of the body to its change in motion, right? So which is why it is important that you wear a seatbelt so that when you are about to move in that direction, the seatbelt will be holding you back so that you do not fly out of the window. So in a worst case scenario, after this happens, you might find that the driver might have hit the windscreen or maybe probably flown out of the window if he was driving at a very, very large speed. Right. Then 7.4 says, state the law of physics, which can be used to explain your answer about the motion of the driver in the previous question. So remember the term inertia that we get it from the law of physics, which is known as Newton's first law. So Newton's first law. Now we are asked to define. So they say, state the law of physics. We know when they say state, that is just definition. So Newton's first law, we say it states that the object or body will continue in a state of rest or uniform motion. So others might say constant velocity instead of uniform motion. So in a state of rest or uniform motion, unless an unbalanced force, an unbalanced force acts upon it. Right. So that's how you define Newton's first law. States that the object or body will continue in a state of rest or uniform motion unless an unbalanced force acts upon it. Now you can write any other relevant definition that you know, but then make sure when it comes to definitions, guys, always put this in the back of your mind. When it comes to your definitions, please download the DBE exam guideline, and then make sure that you have the updated exam guidelines. So make sure that you download the latest. So now that it's 2023, you can download for 2023, 2024, right? So make sure that your exam guidelines are always updated so that you are able to see the definitions that are expected of you in the exam, right? So they want you to write the definition exactly as it appears in your exam guideline. If you don't write it that way, you don't get a mark. So make sure that your definitions are in line with your DBE exam guideline, right? Which is provided by the CAPS document. Now, okay, with all that being said, let's just end our lesson here. Please keep on practicing and then practice more of those questions. Do it just like I do it. Start from the easier questions and then escalate your way up to the exam type questions, and then slowly to those past exam papers, and then to those difficult questions. So always build momentum whenever you are studying or practicing, right? So if you have enjoyed the lesson and you have found this lesson helpful, you know what to do. Press the thumbs up button. And then if you are watching this video and you haven't subscribed, please, please, please do subscribe. And then most importantly, share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning as a team.